Welcome to this explainer. Today we're taking a measured, structural deep dive into a true foundational pillar of enterprise IT, deploying and managing Active Directory domain controllers. Think about it. What happens when you need a new domain controller but your branch office is stuck at the end of a slow, expensive satellite link? Or maybe you're spinning up Active Directory in Azure and you suddenly realize the default networking just doesn't support dynamic DNS. Domain controllers are the heartbeat of your environment. Every user login, every computer account, every Kerberos ticket flows right through them. So placement and deployment methodologies matter immensely, whether you're in a pristine data center, a dusty branch office, or the cloud. Our syllabus for today's lecture covers 4 core areas. First, on-premises deployment phases. Second, branch office solutions. Third, upgrading domain controllers. And finally, deploying in Azure. Section 1, on-premises deployment phases. Okay, let's dive right into this, starting with a standard on-premises installation process. This is the absolute foundation that all our other architectural decisions are built upon. The standard deployment happens in 2 distinct phases. Phase 1 is straightforward. You're simply installing the binaries, the core files that implement the domain controller role. You can do this through Windows Admin Center or your familiar Server Manager interface. But it is vital to understand that at the end of this initial step, you only have the Active Directory Domain Services, ADDS, files sitting on the server. The server is not actually functioning as a domain controller quite yet. Nothing has been configured. And that brings us to phase 2, configuration. This is where the true architectural work begins. The most common approach to phase 2 is launching the ADDS configuration wizard. Now, this wizard forces you to make a series of critical decisions. First, are you creating a new forest, a new tree, or adding to an existing domain? That dictates your entire DNS naming structure. You also must deliberately choose your forest and domain functional levels. These levels set the baseline for capabilities, requiring you to carefully balance modern features against any legacy domain controllers you might still have running. The wizard also asks if this controller should be a DNS server and if it should host the global catalog. Usually, you select both by default to ensure proper forest-wide searches and group resolution. Finally, you'll establish the legacy NetBIOS name and confirm the physical paths for your database and sysvol folders. Within that exact same wizard, there is one mandatory step that requires your full attention: setting the DSRM password. DSRM stands for Directory Services Restore Mode. I want to pause here because this is absolutely critical. This is a special boot mode used specifically for repairing or recovering Active Directory. If your environment suffers a catastrophic failure and you ever need to restore Active Directory objects from a backup, you will boot the affected domain controller into DSRM. And to authenticate, you have to use this exact dedicated password. It is a fundamental element of your disaster recovery posture. Now, everything we just discussed assumes you have a graphical interface, but a server core installation purposefully lacks that local Server Manager GUI. You can't just click through a local wizard. Instead, you have to drive the installation from a different seat. You can utilize Windows Admin Center remotely, script the entire process leveraging PowerShell commandlets, or use remote server administration tools, commonly known as RSAT, from another server with the desktop experience or even a client machine. The underlying process remains identical. It's literally just your management vector that changes. Section 2, Branch Office Solutions. Let's move along and see how this builds into our next topic. We're now pivoting from the pristine, high-bandwidth environment of a centralized data center to the often messy reality of remote locations. This brings us to a fundamental architectural question. How do we successfully deploy domain controllers when we're forced to operate over slow, unreliable, or really expensive wide-area network links? Furthermore, how do we protect our directory when the physical location is unsecure? We're talking about a server maybe just sitting in an unlocked supply closet. Replicating a massive Active Directory database over a constrained satellite link could take days and incur massive bandwidth charges. And putting your entire user database in that unlocked closet, that is a profound security risk. So, to solve the bandwidth constraint, Microsoft provides a brilliant solution called Install from Media, or IFM. The methodology here is highly efficient. You create a backup of Active Directory at headquarters, save it to physical media like a USB drive, and securely transport that physical drive to the branch office. Then, when you run the configuration wizard at the remote site, you select the Install from Media option and point it to that local USB drive. Because the vast majority of the data copying happens locally, the only traffic that must cross that fragile WAN link is security-related information and any incremental changes that occurred since the backup was taken. It is a massive saver of both time and bandwidth. And to solve the physical security challenge, we utilize the Read-Only Domain Controller, or RODC. Think about it. If a standard domain controller is physically stolen, the attacker potentially possesses your entire user database, including all your password hashes. An RODC mitigates this by holding only a read-only copy of the database. Most importantly, by default, an RODC does not cache any user passwords whatsoever. Now, you can explicitly configure it to cache credentials for specific branch users to speed up their local logins, but its default posture completely limits your exposure. If an RODC is stolen, the attacker cannot make changes to Active Directory, and they cannot access uncached password hashes. Section 3. Upgrading Domain Controllers. We now transition to an inevitable lifecycle management task that every systems administrator must eventually face: modernizing underlying operating systems to maintain support and security. When it comes time to upgrade, you basically have two primary strategic options. The first is an in-place upgrade of the operating system on your existing hardware. While this is technically supported from Windows Server 2012 R2 forward, the second method is vastly superior. We strongly recommend the add and retire strategy. In this scenario, you add brand new servers running the modern OS, like Windows Server 2025, into your existing domain as new controllers. Once they are replicating properly, you simply and gracefully decommission and retire the older servers. This approach ensures a pristine, clean installation of both the operating system and the Active Directory database, entirely free of accumulated configuration baggage and legacy craft. Section 4. Deploying in Azure. For our final section, we shift our focus up to the cloud. While all the traditional on-premises rules still apply, Azure Infrastructure as a Service introduces specific, rigid considerations that must be respected. Let's detail these rigid cloud requirements. First, Active Directory requires a proper network topology. You must deliberately create an Azure virtual network and attach your virtual machines to it. If you are extending an on-premises environment, this dictates the absolute need for a hybrid connection, either a site-to-site VPN or an express route circuit. Second, you must map your AD/DS site topology to correspond exactly with your Azure Virtual Network IP ranges to optimize replication traffic. Finally, and this is crucial, Azure virtual machines default to DHCP. Domain controllers, however, demand stability. You must configure static IP addresses within Azure so that those addresses persist through virtual machine reboots and routine maintenance events. Now, DNS is where a lot of cloud deployments stumble. Active Directory Domain Services relies heavily on dynamic DNS and specific service resource records to function properly. The default, built-in Azure DNS service simply does not support dynamic updates. Therefore, you cannot rely on it for your domain controllers. You must bring your own solution. The most straightforward approach is to install the Windows Server DNS role directly onto your Azure domain controllers, exactly as you would on premises. Alternatively, you can utilize Azure Private Zones, provided you configure them correctly for your specific architecture. I really want to draw your attention to this specific quote regarding disk configuration in Azure, because getting this wrong can be catastrophic. When you deploy a domain controller in Azure, you should place the NTDS.DIT database file and the sysvol folder under a separate, dedicated data disk, not the operating system disk. Most importantly, you must set the host cache preference for that specific data disk to none. Active Directory employs its own highly specific caching and transaction logging mechanisms. If you allow host-level caching and that virtual machine loses power or crashes unexpectedly, you risk severe data corruption. Setting the cache preference to none ensures that all write operations are committed directly and safely to durable storage. We have traversed the foundational phases of installation, the strategic adaptations required for branch offices via IFM and RODCs, the clean lifecycle management of the add and retire upgrade method, and the strict networking and disk rules for Azure deployments. Mastery of these structured scenarios is not just academic, it is the exact knowledge required to pass rigorous certifications like the AZ-800 exam and to protect real-world enterprise environments. So, I leave you with this question to consider. Are you ready to architect secure, efficient ADDS deployments across any environment the real world throws at you? Thank you for joining this explainer.